Welcome to the deep dive. Today, we're doing something really practical, I think.
Yeah, what do we got?
We've got a set of practice questions from the PCED 30-01 exam.
Ah, okay. Interesting.
And honestly, even if you're not thinking about that exam at all, these questions, they're gold mines for understanding, the core ideas of handling data.
Absolutely. It's a good way to ground the concepts.
Think of it as a sort of fast track to getting a solid handle on working with data effectively.
Right. Forget the dry theory for a bit. We're using these actual questions to pull out the real-world knowledge you need.
From start to finish.
Pretty much. Like how data gets collected, how we clean it up, analyze it, even visualize it.
And the goal is just to make these key concepts really clear and, well, useful, right? No matter your background.
Exactly. Make it applicable.
Okay, let's dive right in then. First question is about getting the data in the first place. What is the main benefit of using automated data acquisition tools?
Okay. And the answer?
The answer, according to this, is A. They reduce manual effort and increase efficiency. Now, saving time, that's obvious, sure. But what's the bigger deal here?
Well, it's the scale, isn't it? The sheer amount of data flying around today.
Right.
I mean, people talk about generating more data daily now than like in all of history before the 2000s. It's staggering.
Wow. Okay.
So trying to collect that manually, just impossible for most things. Automated tools aren't just nice to have, they're often the only way.
So like sensor networks or real-time systems?
Exactly. Think environmental monitoring,
Okay.
stock market feeds, stuff that needs constant, reliable data streams.
Mm-hmm.
Automation gives you that consistency and speed, and it cuts down on, human error during entry.
Makes sense. So it's really fundamental for dealing with modern data volumes.
Totally.
Okay, question 2 then. This shifts to what happens after we get the raw data. Which of the following best describes data transformation?
And the answer here is,
B, converting raw data into a more suitable format sounds straightforward, but why is it so critical?
well, think about cooking. You get raw ingredients, right?
Yeah.
You don't just chuck them in a pot.
Yeah.
You prep them. Chop, peel, maybe marinate.
Okay, I see the analogy.
Data transformation is that prep stage.
Yeah.
Raw data, it's often messy, inconsistent formats, errors, maybe missing bits.
Mm-hmm.
If you don't transform it into something clean and standard, your analysis, it's going to be shaky. Garbage in, garbage out, basically.
So give us some concrete examples of this. Data chopping and marinating, what are we actually doing?
Oh, all sorts of things. Like dates might be recorded in 10 different ways.
Yeah.
MDY, YYY, MMDD, whatever. Transformation makes them all the same.
Okay.
Or units, temperature in Celsius here, Fahrenheit there.
Yeah.
Got to convert them.
Right. Standardization.
Yeah, or maybe summarizing data, like turning daily sales figures into monthly totals. That's aggregation. Or even converting text labels, say red, blue, green, into numbers, if your analysis tool needs that.
So it's really about getting everything consistent and ready for the actual analysis tools.
Precisely.
Yeah.
Getting it into a usable state.
Cool. Okay, question 3 moves into finding the weird data points. Which of the following is a typical technique for detecting outliers? The answer is C, Z-score method.
Ah, outliers. Always fun.
So we're looking for data points that are way off from the rest. Why does that matter so much? And how does the Z-score thing work?
It matters hugely because outliers can seriously distort your results. Imagine calculating average income, like you mentioned.
Yeah.
And you've got one billionaire in a neighborhood of people earning, say, $50K a year.
Okay.
That one outlier completely skews the average, makes it look much higher than it really is for most people.
Right. Gives a misleading picture.
Totally. The Z-score method is a statistical way to spot these extremes. It measures how many standard deviations a specific data point is away from the mean, the average.
Standard deviations, right.
So a really high or really low Z-score flags a point as being statistically unusual, far from the center of the data distribution. It's a common first check.
Got it. A mathematical way to flag the extremes that might be messing things up. Okay, question 4. Pre-processing, but specifically for machine learning. What is a key reason to use feature scaling in machine learning pre-processing?
And the answer.
B, to standardize the influence of different features. So why do features need to be on a level playing field for ML algorithms?
Okay, think about predicting house prices again. You might have features like square footage ranging from maybe 500 to 5,000.
Big range.
And number of bedrooms, usually like 1 to 5, maybe 6. Much smaller range.
Right.
If you feed those raw numbers into certain algorithms, especially ones based on distance.
Like K nearest neighbors? Or SVM?
Exactly. Those, they might just naturally give way more importance to the square footage simply because the numbers are bigger.
Ah, okay. The scale itself biases the algorithm.
Precisely. Feature scaling techniques, like normalization squeezing values into a 0 to 1 range, or standardization centering them around 0. They bring all features to a similar scale.
So the algorithm weighs them more fairly based on their actual predictive power, not just their initial size.
That's the idea. It prevents one feature from dominating just because its units are larger. Crucial for many models.
Makes sense. Okay, question 5 is about making our data richer. In data analytics, what does data enrichment involve? The answer is C. Enhancing data by adding relevant external sources.
So going beyond just cleaning what you have.
Yeah, adding more info. How does that work practically?
It's like adding layers of context. Super valuable. Imagine you've got customer purchase data, just who bought what.
Okay.
Now, what if you enrich that by adding, say, demographic data or maybe geographic info based on their address?
Like census data or something.
Could be public data, maybe purchase third-party data.
Yeah.
Suddenly you might see patterns you missed before.
I agree.
Like maybe customers in urban areas prefer product X, while rural customers prefer product Y. Or perhaps a certain age group is your main buyer for a new item.
Ah, so it allows for much deeper segmentation and understanding.
Exactly. More context leads to better insights, more targeted actions, more personalized experiences. It really boosts the value of your original data.
Cool. Adding layers to the story, as you said. Okay, number 6, visualization. Which visualization is most effective for displaying a correlation between two numerical variables? Answer: A, scatter plot.
The classic.
Why is this the go-to for seeing if two number-based things are related?
Because it's designed exactly for that. Each dot on a scatter plot represents one observation, one data point. Its position on the horizontal x-axis is one variable's value, and its position on the vertical y-axis is the other's.
Oh, okay.
So you just look at the cloud of points. Do they seem to form a line? Is it sloping upwards?
Positive correlation. As one goes up, the other tends to go up.
Right, or sloping downwards.
Negative correlation. One goes up, the other tends to go down.
Exactly. Or is it just a random blob of dots?
No obvious linear correlation then.
Yep. It gives you that instant visual intuition about the relationship. Super important for things like regression, understanding drivers.
Gotcha. Visual check for relationships. Number 7 gets a bit more advanced. What is the main goal of using principal component analysis, PCA? Answer: B, to simplify a data set while retaining key information.
Ah, PCA. Dimensionality reduction.
Simplifying complex data
So-
sounds useful. How does it actually work? How does it simplify without just throwing away info?
It's clever. Imagine you have data with tons of features, maybe hundreds or thousands. Many of those features might be correlated, telling you similar things.
Okay, redundant info.
Kind of. PCA finds a new set of artificial features called principal components. These new features are combinations of the old ones, and they're designed to be uncorrelated.
Right.
And crucially, they're ordered. The first principal component captures the most possible variation in the original data. The second captures the next most variation that wasn't captured by the first, and so on.
So you get the most important patterns first.
Exactly. So often you can keep just the first few principal components, maybe 2 or 5 or 10, and they'll still represent a huge chunk, maybe 90% or 95% of the original information, the original variance.
And you've gone from hundreds of features down to just a few.
Yep. Reduces complexity, can filter out noise, makes models train faster, all while keeping the essential structure of the data. It's like finding the main themes in your data set.
Very cool. Distilling the essence. Okay, question 8 brings us back to basics, but crucial basics. What does data validation ensure? Answer: B, that data meets quality and format standards.
The gatekeeper step.
Yeah, sounds like it. What kind of problems does validation actually catch for us?
Oh, all the fundamental stuff.
Mhm.
Are required fields actually filled in?
Okay, completeness.
Is the data type correct? Numbers in a number field, not text?
Right.
Are the values within a plausible range? Like an age field shouldn't have 200 in it. Or
Yeah.
negative numbers.
Sanity check.
Exactly. Checking for consistency across different related tables, perhaps. It's all about setting up rules and checks before you analyze to make sure the data you're relying on is actually accurate and usable.
Prevents garbage getting into the analysis pipeline later on.
Precisely. Foundational for trustworthy results.
Absolutely. Okay, question 9 looks at different kinds of data. Which of the following is considered unstructured data? The answer given is D, social media posts.
Ah, the messy stuff.
What makes it unstructured, and why is it harder to deal with?
Unstructured data just means it doesn't fit neatly into a predefined model, like rows and columns in a spreadsheet or database table.
So no neat boxes.
Right. Think about a social media post. It can have text, right? Free-form text,
Yeah.
plus maybe an image or a video link, hashtags, emojis, user mentions. It's a mix of different things, no fixed format overall.
Okay, I see. Compared to, say, a sales record with specific fields for product ID, quantity, price.
Exactly. That's structured. Because unstructured data lacks that predictable format, you can't just query it easily with standard database tools.
Oh, how do you analyze it?
You need different techniques. For the text, things like natural language processing, NLP. For images, computer vision, it's a whole different ballgame. And there's so much unstructured data out there now.
Right. Emails, documents, audio files, lots of it.
A huge amount.
Okay, makes sense. It's the freeform stuff. Last question, number 10. Back to preprocessing. During preprocessing, what is the purpose of binning continuous data? Answer: A. To reduce noise and group values into intervals.
Binning or discretization.
Why would we take nice, detailed, continuous numbers like someone's exact age and lump them into broader categories, like age groups? Seems like losing detail.
You are losing some detail, that's true. But sometimes that's useful.
Why?
Well, for one, it can make patterns easier to spot, especially in visualizations. A histogram with age bins might show a clearer distribution shape than plotting every single individual age if you have thousands of people.
Okay, simplifies the view.
It can also reduce the impact of minor variations or noise. If someone's age is 34 or 35, maybe for your analysis, putting them both in the 3039 bin is sufficient and smooths things out. And some modeling techniques actually prefer or require categorical inputs rather than continuous ones. So binning can be a way to prepare data for those specific algorithms.
So you trade precision for maybe simplicity, noise reduction, or compatibility with certain methods.
That's a good way to put it. It's another tool in the pre-processing toolkit.
All right. So maybe a final thought for you, the listener, to chew on.
Yeah.
Think about a real project, maybe something you've worked on or could imagine. How would these different techniques we've talked about, automation, validation, transformation, enrichment, PCA, visualization, how would they actually fit together?
Good question.
What new possibilities or maybe even challenges pop up when you think about combining, say, automated data streams with really rigorous validation and then using something like PCA before you try to visualize the main trends? How does the whole pipeline work together?
Yeah, considering the interplay, that's where the really interesting stuff happens. Lots to think about there.